Welcome to lecture 7 of flow of water through soils. In the previous lecture, we have introduced the flow net concept and then we constructed methodology for predicting the rate of seepage through isotropic materials. In this lecture, let us look into how we can solve some problems by using the concepts which we have discussed in the previous lecture. Then we extend our knowledge for calculating the rate of seepage through anisotropic material, being anisotropic in the sense from the permeability point of view, having different permeabilities in horizontal and vertical direction. Thereafter, we will look into how we can calculate the rate of seepage through an earthen dams. So, let us look into this particular concept once again, the flow net method of construction. So, here for determining the seepage, the flow net solution, the computation of the rate of seepage, we discussed that it is formed by the two orthogonal two families of curves. One is formed by equipotential lines and flow lines. The space between any two flow lines we called as flow channel, and the head difference between any two equipotential lines we called as potential drop. So, based on this equipotential drops between two flow lines is delta H is equal to HL by ND, HL by ND, ND is the number of the potential drops. So, from the Darcy's law, if you again apply, then we said that Q is equal to K into HL, HL is the total head loss which is occurring, NF by ND, that is number of flow channels to number of this potential drops to A into B is nothing but the aspect ratio. So, we said that while constructing the curvilinear squares, this aspect ratio is be maintained as 1. So, let us look into a problem. So, flow net around horizontal drain. Let us consider in this particular slide what you are seeing, a drain which is found at 3 meter from the top surface, which is placed in sand, having coefficient of permeability 5 into 10 to the power of minus 7 meter per second, isotropic in nature, and the center of the this drain is 3 meters from the top surface. The water table is found to be at the top surface itself. The free water surface is found to match with the top surface of the soil. So, the depth of the soil which is under consideration is around 6 meters. So, this is the long horizontal drain. So, here what we are considering in this problem is a long horizontal drain. So, this particular aspect also can be now studied as a two-dimensional problem. So, in this case now, if this is the x direction, this is the z direction, then this again turns out to be a two-dimensional problem. Now, consider this top surface of the soil or top surface of the water as datum. Now, by using this flow net concept, if you look into it, we can draw flow nets. Keeping in view of the symmetry, the central line, you can see here the stream of equipotential lines and flow lines. So, the flow takes place like this in this direction because the head loss occurs in this direction. So, the flow occurs in this direction and then this drain tries to divert the water from this. So, we are interested in finding out the rate of seepage and then this particular pore water pressure at this particular location x here, which is shown in this slide, and also the velocity of the flow. So, this 3 meter is the center and this is the flow net and this is the symmetry. So, you have got a two symmetrical mirror image type flow nets which are shown here. So, here what you are seeing, this is the first equipotential line, second, third, 4, 5, 6, 7, 8, 9. So, by the time here if it comes, the head which is there for the flow to take place is around 3 meters. So, when the flow which is actually commencing from here, so it is in the flow is this direction. So, as per our conventional numbering, we numbered like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Similarly, this side. Then flow channels. So, this is the first flow channel, second flow channel, third, 4, 5, 6. So these are the number of the flow channels which are determining this particular flow. So this is in this slide what we are trying to do is that rate of flow net construction, for example a long horizontal drain, and that is can be considered as a two-dimensional problem. So let us look into the solution. So flow net around the horizontal drain, that is the example under consideration for us. Find the discharge to the drain in meter cube per day per meter length of the drain. So per meter length of the drain, so suppose if the drain is of 100 meters, then it can be, we can calculate by using this concept. So considering the datum at the free water surface, so this makes the total head at the top of the ground is 3 meters. With that, the total head at the top of the ground is around 3 meters. So HL, that is head loss from the surface to the drain, it is around 3 meters. So by considering only one half of the flow region, so keeping in view of the symmetry, consider only one half of the flow region. If you count, then number of flow channels are 6, number of potential drops are 9. And being isotropic in nature, we can use Q is equal to K HL into NF by ND. Being symmetrical isotropic, being curvilinear squares, the aspect ratio A by B can be assumed as 1. So by substituting now these values, the K is the coefficient of permeability and H is the head loss, and number of flow channels, number of potential drops, and multiplied by 2 because we have the two flow regions determining this longitudinal drain. So multiplied by 2, which gives us 0.1426 meter cube per day per meter run of the pipe. This is the rate of seepage or rate of discharge which can occur in per meter run of the pipe. So by using this concept of flow net construction, simple problems like the drain problem, which we consider and we treat it as a two-dimensional problem, and it can be solved. Now flow net around the horizontal drain, and the same problem which we continue now. Find the pore water pressure at X 1.5 meter into the soil directly above the drain. That means that if you go into the previous slide, this is X, which is 1.5 meter below the ground surface and directly above the center of the drain. So there we are required to determine what is the pore water pressure. So if you look into this, potential drop between two equipotential lines is around 3 by 9. So N is the number of total potential drops, and head loss is around 3. So potential drop between any two equipotential lines is around 3 by 9. The total head at X, that location X, which is 1.5 meter below the ground surface and above the center of the drain, that can be given by total head at 6 is equal to 5.6 by 9 into 3. So the total head at X which is available is around 1.867. That means that it started with 3, by the time it came here, that much head is already dissipated in the form of a flow which is taking place through the soil. So elevation head at X is 1.5 meter because the datum is at the ground surface, so elevation head is 1.5 meter. So pressure head at X is equal to, by using total head is equal to pressure head plus plus elevation head. From there we get 0.367 meters as the pressure head at X. So pore water pressure at X is equal to 0.367 into 10, around 36.7 kg per meter square, by treating this unit weight of water as 10 kilonewton per meter cube. So that is how we can determine pore water pressure at different locations. If you know the where exactly the pore water pressure is required, and if you know from this construction, we can estimate what is the head at a particular point. From there, by looking into the elevation head, we can calculate the pore water pressure at a particular location. So this is an example which demonstrates, but by using the same concept, we can determine the pore water pressure at different locations. So estimate the velocity of the flow at X. So we are also been asked to determine velocity of flow at X, that location. So let the vertical length of the curvilinear square at X is around 0.4 meters. So let us assume when this particular flow net is drawn to a scale, we can easily get the vertical length of the curvilinear scale at location X. If that happens to be 0.4 meters, then now the hydraulic gradient is nothing but 0.33. That is because head drop between any two equipotential lines is around 3 by 9, that is 1 by 3 is around 0.33, that divided by the length of the flow, that is around 0.4 meters. So, with that the hydraulic gradient is obtained around 0.83. By using now the Darcy's law, V is equal to K I, K is known to us and I is known to us. From that we can get, see, the velocity of the flow at x is given by 4.75 into 10 to the power of minus 7 meter per second. So, in this problem what we try to do is to determine the seepage or a discharge through pipe per meter length, and then by treating that long horizontal drain has a two-dimensional problem, we constructed flow net and it has got two flow regions. So, by using the concept of the method of flow net construction, the flow nets are constructed by approximating as a curvilinear squares, and then we determine the number of flow channels and number of potential drops. Then we try to obtain the seepage, and from there we try to calculate the pour water pressure at a particular location which has been asked in this particular problem as x, and then we try to calculate the velocity at a particular location x. So, having discussed the flows in isotropic materials, let us try to look into the flow in anisotropic material, that is the flow nets in anisotropic material, how to deal about this. So, in developing the procedure for plotting flow nets, we assumed that permeable layer is isotropic. That means that K horizontal is equal to K vertical, being a two dimensional, K horizontal is equal to K vertical we assumed, which is equal to K. So, that is isotropic as far as permeability is concerned. Consider the case of constructing flow nets for seepage through soils that show anisotropy with respect to permeability. So, now consider the case of a constructing flow nets for seepage through soils that show anisotropy with respect to permeability is concerned. Anisotropy with respect to permeability concerned means the K horizontal is not equal to K permeability. So, in that case what we should do and how to construct the flow nets. So, for two dimensional problems, when say K horizontal if it is equal to Kx, K vertical if it is equal to Kz, then we can write from Laplacian equation as Kx is equal to dou square h by dou x square plus Kz into dou square h by dou z square is equal to 0. That is for two dimensional problems. In case of isotropic problems, what we said is that Kx is equal to Kz is equal to K and not being equal to 0, we said that dou square h by dou x square plus dou square h by dou z square is equal to 0 is the Laplace equation for a two dimensional problem. But in case of anisotropicity, as far as from the permeability is concerned, Kx into dou square h by dou x square plus Kz into dou square h by dou z square is equal to 0 is a Laplacian equation. Now, the same equation by rearranging the terms, we can write in the form of equation A, which is shown here as Kx by Kz into dou square h by dou x square plus dou square h by dou z square is equal to 0. A closer analysis of the above equation indicates that a simple Laplacian equation may be endangered if adequate change of variables is used. So, let us try to write the same equation by substituting x is equal to, that is capital X is equal to small c times x. Capital X is equal to small c times x, where c is a constant. Now, by writing this now, dou square h by dou x square plus dou square h by dou z square. So, with that, by substituting for x is equal to cx, we can write the same equation dou square h by dou cx whole square plus dou square h by dou z square, which can be written as 1 by c square into dou square h by dou x square plus dou square h by dou z square is equal to 0. So, let us call this as the equation of the form which is indicated by B. So, now comparing the equations A and B, the constant c can be identified as now as c is equal to root over kz by kx. By comparing the equations A and B in the previous slide, we can obtain the constant c, which is identified by comparing the equations A and B as c is equal to root over kz by kx. So, equation B is of the same form as dou square h by dou x square plus dou square h by dou z square is equal to 0. So, which governs the flow in isotropic soils and should represent the two sets of the orthogonal curves in capital X small z plane. So, the Z is again same, but X is now which is different because we are now trying to convert anisotropicity into some transformed section. So, here the X is equal to which is nothing but C times X. Now, the C if you substitute for root over kz by kx, we can write capital X is equal to root over kz by kx into small x. So, now consider now the flow nets in anisotropic material. So, if the flow through the natural anisotropic section if you take, and this will be look like this, which is L and then same depth D, assuming that the flow is taking place in the vertical direction along that is in the Z direction or Z axis. Kz is the permeability along the Z axis, and the flow is occurring over L into 1 meter, that is per meter length of a plane which is considered here. So, in this case permeability is occurring over a flow is occurring over an area of L into 1. So, assumption is that anisotropy merely causes a linear distortion of the flow net. On the assumption that anisotropy merely causes the linear distortion of the flow net, the flow through the natural anisotropic section which is shown here, D is the depth and L is the length, and Kx is the flow which is along the x direction, Kz is in the vertical direction, that is Z direction, and Q is the flow amount of flow which is occurring through this. Now, flow through the transformed section, if you look into it, because we have to now convert that into a permeability which is isotropic in nature. So, for that let us assume that Kt is the transformed permeability which is in both in horizontal and horizontal direction as well as in the vertical direction. So, if that is the case, then the flow through the transformed section which is again converted into isotropicity, that anisotropicity is converted into isotropicity by considering a which is called a transformed permeability. So, in that case this length is now taken as L into root over kz by kx. Still to satisfy again, even with this also, with the transformation whatever we are doing, we should see that again the Laplacian equation is satisfied. So, here the length is now L into root over kz by kx, and which is small, being because we have already discussed that kx is always more than kz. That is under the assumption that horizontal permeability is more than vertical permeability. Now, starting with the natural section, that is on the left hand side in the previous slide, the flow quantity per unit length can be written as Q is equal to L into 1, that is area over which the flow is occurring, into Kz, that is the permeability, and I is the hydraulic gradient with which the flow is occurring. That is, let us write that equation as C. Within the transformed section now, the same quantity of the flow is calculated as follows, but now that L which is now this transformed length, which is nothing but L into root over kz by kx into 1, that is the area through which the flow is occurring, with a permeability Kt, but same hydraulic gradient I. Now, comparing C and D, if that the second with the transformed section the same quantity of the flow is calculated, and if that is indicated as C, and comparing C and D, the transformed permeability can be obtained as now Kt is equal to root over kx kz. So, the transformed permeability, for example, if the anisotropicity is there and if kx is not equal to kz or k horizontal is not equal to k vertical, the transformed permeability can be obtained by considering the square root of kx and kz or k horizontal into k vertical. So, the same expression could have been found using the flow in horizontal direction. So, in the previous slide, if you would observe, we have considered the flow in the vertical direction. The same thing would have been considered if you consider the flow in the horizontal direction. But note that then the hydraulic gradient changes from I is equal to h by L in the natural section to I is equal to h by L into root over kz by kx in the transformed section. So, steps involved in the construction of the flow net in case of a soil which is having anisotropicity in nature, and as far as the permeability concerned is to plot the section of the hydraulic structure, adopt a vertical scale. So, first any hydraulic structure under consideration is there. So, plot the structure with vertical scale and determine ratio of root over kz by kx, that is nothing but root over K vertical by K horizontal. Once the ratio is obtained, now adopt a horizontal scale such that horizontal scale is root over kz by kx times the vertical scale. That is, the horizontal scale is root over kz by kx times the vertical scale. So, here for the steps involved in the construction of the flow net in an anisotropic medium are as follows. To plot the section of the hydraulic structure, adopt a vertical scale, determine root over kz by kx is equal to root over k vertical by k horizontal, and adopt a horizontal scale such that scale horizontal is equal to root over kz by x into scale vertical. Now, the next step, with the scales adopted in step 1 and step 3, plot the cross section of the structure. Now, with the scales adopted in step 1, that is vertical scale, that is same, and that previous step 3 we said that scale horizontal is equal to root over kz by kx into scale vertical. So, draw the flow net for the transformer section plotted in step 4 in the same manner as is done for the seepage through isotropic soils. So, now what we have done is that this anisotropic medium we converted into a transformed section in the form of a representing the isotropicity, and for that we have accounted the variation in horizontal direction, vertical direction by considering transformer permeability Kt is equal to root over Kx and Kz. So, calculate now the rate of seepage as Q is equal to root over Kx Kz, because now the transformed permeability is under consideration, which is nothing but the square root of Kx and Kz, and H is the head loss and Nf by Nd. So, by using this now we can determine the rate of seepage. Now, having looked into the theoretical aspect, let us look into an example problem for the flow nets in anisotropic material. So, consider a concrete dam which is like this, and a cutoff sheet pile wall is shown here. Basically, this type of cutoff sheet pile walls are provided to control seepage pressures. As indicated here in this slide, to control seepage pressures, these cutoff sheet pile walls are driven. Sometimes you have got these cutoff sheet pile walls even on the upstream side as well as on the downstream side. In this case, only it has got an upstream side, and sometimes this also it is you practice to even to provide cutoff sheet pile walls on the downstream side also. So, consider a concrete dam on a layer of a homogeneous anisotropic clay having Kx is equal to 16 into 10 to the power of minus 8 meter per second, and Kz is equal to 1 into 10 to the power of 8 meter per second. So, x is this direction and the z direction is vertical direction. So, x is the horizontal direction and z is the vertical direction. The length from here to here is 12.8 meters, and 5 meters is the head which is available on the upstream side, and the depth of the cutoff sheet pile wall is 4.6 meters, and the tip is 6 meters above this impervious rock under consideration. So, from the flow net what we require is that flow quantity seeping on the downstream side of a dam, that is seeping through the soil. So, now having seen, now let us we have got permeabilities now, Kx value which is around 16 into 10 to the power of 8 meter per second, and Kz is 1 into 10 to the power of 8 meter per second. So, determine C now, that is nothing but root over Kz by Kx, which is nothing but a 1 by 4. Now, the transformed permeability is nothing but root over Kx and Kz, that is 4 into 10 to the power of minus 8 meter per second is the transformed permeability. Now, as per the procedure, if you look into it, if you draw with the anisotropic medium, you will get the flow nets like this, and the curvilinear rectangles of a sides ratio root over Kx by Kz. So, what we get here, they are not squares, they are not orthogonal. So, the reasons we are going to discuss, but the curvilinear rectangles of a sides of a ratio are shown here, and what you see here is again flow nets, but in a distorted, in a natural section with a anisotropicity. The effect of anisotropicity reflected like in this form. Now these equipotential lines and flow lines do not cross at right angles, as the tangent to flow line does not correspond to the normal to the equipotential line, as was the case for isotropic soils. Unlike the isotropic soils, if you look into this, equipotential lines and flow lines do not cross at right angles, as the tangent to flow line does not correspond to the normal to the equipotential line, as was the case for isotropic soils. Hence, the flow net is basically harder to sketch because the sides of every quadrangle in the net must have a ratio of around root over k's by kz. So, the flow net is harder to sketch. So, because every quadrangle in the net must have a ratio of root over kx by kz. So, hence actually we are better to resort to the transformed section. So, how to construct a transformed section is that, so first to construct a hydraulic structure by adopting a vertical scale. So, by adopting that, if you draw, the vertical scale is same, but if you look into it, this is a flow net which is for a transformed section. So, here what we did is that the horizontal scale is now, that is 12.8 meters, which is now reduced to 1/4 times, because now the transformed section scale we adopted, scale horizontal is equal to root over k, that is 1/4 times scale vertical. So, if you put into it, so what we get is around this particular 3.2 meters in a transformed section. But keep again the height, again vertical scale, that we are not touched up. Now, based on this, now if you construct flow lines, again by fulfilling the same requirement that this orthogonality and all these things like in isotropic problems, this transformer section is nothing but an isotropic problem now. So, with this now if you compare, now 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, number of potential drops are 10. So, ND is equal to 10. Now, if you look into this 1, 2, 3, 4, 5. So, if this is also approximated as a on flow channel, so we have got number of flow channels in this particular flow region for this structure in the transformed section, there are around 5. And head which is occurring, the loss which is total head loss is around 5 meters. So, Q is equal to KT into H into NF by ND, which is around now 10 to the power minus 7 into meter cube per second per meter. So, this is how we treat soils with anisotropicity in nature, and particularly in 2-dimensional problems, where what we do is that we convert them into a transformed sections and draw the same flow nets and then determine the rate of seepage, and the procedure is again is very similar to the one which we discussed already. Now, having discussed for confined problems like this in the previous slides, how we can determine seepage through dams, earth dams or embankment dams. Example, this embankment dam or earth dam, the flow which is nothing but is an unconfined seepage. So, the example of an unconfined seepage means the seepage through embankment dams is an unconfined seepage. For example, if you consider in the previous slide like flow through a sheet pile wall, that is again comes out as confined seepage. So, here one boundary of the flow region being a phreatic surface on which the pressure is atmospheric. So, here in this case what happens is that in the unconfined seepage, one boundary of the flow region being a phreatic surface on which the pressure is atmospheric. So, the phreatic surface constitutes the top flow line and its position must be estimated before drawing the flow net. The phreatic surface constitutes the top flow line and its position must be estimated before drawing the flow net. So, here in this flow through earth dams, the arriving at the phreatic line itself involves a tedious procedures. Otherwise, again the concept of again determining seepage or rate of flow through the dam is very similar, but the tedious procedures which are involved is that to arrive at the phreatic surface, to locate the phreatic surface and to draw the phreatic surface and then construct the flow lines and equipotential lines, and then again we can use the same concept to determine the rate of seepage through a dam. So, calculation of the seepage through an earth dam resting on impervious base. So, if the this dam which is resting on an impervious base, then several solutions have been proposed for determining the quantity of seepage through a homogeneous earth dam. The popular solutions which are discussed here, they are Jupit's solution and Schaffernaks solution and Casagrande's solution. So, in this lecture in the same order we will try to discuss this Jupit's solution and Schaffernaks solution, and then the graphical method which is involved for the Schaffernaks method, and Casagrande's solution which is widely used for locating the phreatic surface. So, here the Jupyter's solution for the flow through in earth dam, that is Jupyter's solution for the flow through in earth dam can be given as like this. The assumption which is involved in this slide which is shown here, a cross section of a earthen dam which is shown, and this is the crest and this is the base and this is the upstream phase and this is the downstream phase. This is called upstream water with a head H1, and the downstream, that is also called tail water level, which is called H2. Z, this x direction and this x direction, and this resting on impervious base. So, this is the toe of the dam, and B is the location here, and the slope which is dz by dx, and this is the phreatic surface. So, the what assumption which is involved in the Jupyter's case is that hydraulic gradient I is equal to slope of the free surface and is constant with the depth. So, we consider I is equal to dz by dx, I is equal to dz by dx was considered by Jupyter. So, if it is assumed that the flow is taking place again as a two dimensional problem if you treat, and q is equal to k into dz by dx. dz by dx is nothing but the slope of this that particular phreatic surface, that is dz by dx, k into dz by dx into z into 1. So, z is this depth here and 1 is the perimeter length of the dam. So, q is equal to k into dz by dx into z into 1, where k is the coefficient of permeability, which is again isotropic, that is what which is assumed because it is constructed with a homogeneous material. So, it can be assumed as kx is equal to kz is equal to k. Now, by separating the variables, we will get q dx and kz dz. If you integrate between 0 to d, that is from 0 to d, that is d is this particular distance from here to here is d, and h1 to h2, that is h2 to h1. Suppose if the tail water level is 0, then you will integrate from 0 to h1. In this case, there is a h2, so h2 to h1 and a kz dz. So, with that, now if you estimate the q is equal to k by 2d into h1 square minus h2 square. After integration and then simplification, we get an expression for q, that is for calculating the flow through a dam by using the Jupyter's solution, which is given by q is equal to k by 2d into h1 square minus h2 square, which again represents the equation for a parabolic free surface. So, the Jupyter assumes that this particular phreatic surface is a parabolic free surface, but in Jupyter's solution some limitations are no attention for entrance and exit conditions. So, no attention has been paid for entrance and exit conditions, no attention has been paid for entrance and exit conditions, because there are certain cases like if you look into here, this is an equipotential line where the orthogonality which is required between this flow line, that is this top phreatic surface, which is not maintained here. Similarly, at the exit conditions also a similar phenomenon reflects here. And if H2 is equal to 0, the phreatic line would intersect the impervious base. So, in the Jupyter solution, if H2 is equal to 0, the phreatic surface will come and intersect with the impervious base, which is again happens to be a flow line. So, that cannot happen. So, these are some of the limitations with the Jupyter solution. Now let us look into the Schaffernaks solution, how it works out. The Schaffernaks solution for the flow through in earth dam, assumption that phreatic surface will be like line AB and will intersect at a distance L from the impervious base. So, in the previous case we have discussed about a limitation that if H2 is equal to 0, the phreatic surface will intersect the impervious base. So, here what the Schaffernaks has considered is that it is intersecting at a distance L from the point O. So, here phreatic surface will be like a line AB, which is shown here, and will intersect at a distance L from the impervious base. So, now we are interested to determine what is this length L, and this is beta, which is that slope of this, and dz by dx, and A is this point. So, from here to here, now that is the distance d, and h is the upstream head, that is now here H2 is equal to 0 and H1 is equal to H. Now this converts to, this is H. So by considering the triangle OBD, so this Z is equal to L sin beta. So if you look into it, this is Z is nothing but now L sin beta here. Now by considering the triangle OBD, I is equal to, it is written here, the Schaffernaks assumes that I is equal to dz by dx is equal to tan beta. So by considering the triangle OBD, Q is equal to kz into dz by dx, we can write K into Z is written as L sin beta, that is here, into tan beta. Tan beta dz by dx, the hydraulic gradient is assumed by Schaffernaks as tan beta. So by simplifying now, we obtain L. So by knowing L, we can determine now Q is equal to K into L sin beta into tan beta. So Q is equal to K L sin beta tan beta. So L is given after simplifying this expression, we get L is equal to d by cos beta minus square root of d square by cos square beta minus h square by sin square beta. So this is an expression where d is this distance and h is the head, beta is the slope inclination. So by knowing L now, we can determine Q is equal to K into L sin beta tan beta. So this is a method, theoretical method for determining L, that is the location where this is intersecting, and again he assumes that AB is the phreatic surface and it hydraulic gradient is assumed as I is equal to dz by dx is equal to tan beta. Now the graphical construction procedure for the Schaffernaks solution is also given for locating again the same L, that is here in this BC the distance. So in this figure here, a cross section of an earthen dam is shown here, and AB is the phreatic surface which is indicated here, and BC is the distance above which it is located, that is now BC is equal to L, which is required to be determined, and this is the impermeable base. So if now what the procedure which is involved, that graphical construction procedure for the Schaffernaks solution is extend BC downwards. So extend BC downwards and draw a vertical line AE and will intersect the projection of line BC at F. Draw a vertical line AE which intersect the extension or the projection of a line BC at F. So draw a vertical line through AE and extend backwards this BC so that it meets at F. With FC as diameter, draw a semicircle FHC. So with FC as diameter, draw a semicircle FHC. Draw a horizontal line AG. Draw a horizontal line AG. With C as center, CG as radius, draw an arc GH. With F as center and FH as radius, draw an arc BH. Draw an arc BH. So with this now, once you locate B, that distance BC is nothing but L. Then by knowing L, then again we can determine the rate of flow through an earth dam by using Schaffernaks solution. Now the third method or third solution which is available for locating the phreatic surface, which is also widely used, is Casagrande's 1937 solution. Casagrande 1937 shown experimentally that the parabola AB actually starts from point A dash, which is indicated in this slide here. So previously all other investigators, Jupit and Schaffernaks, they are not given enough attention to the entrance and exit conditions. Schaffernaks to some extent has considered this exit of the phreatic surface, but if as far as the Jupit is concerned, which is very in the where entrance and exit conditions are ignored. So here Casagrande, which has shown experimentally that parabola AB actually starts from the point A dash. So A dash and A, the distance which he experimentally which has shown that, which is around 0.3 times delta, where delta is this particular length, this horizontal distance delta is from here, from the toe, from this distance, from this point to this point is delta. With this modification of modification value of d, then a dash c is the periodic surface now. So Casagrande suggested I is equal to dz by ds, because dz is that vertical distance and ds is the length along which the flow is taking place. So Casagrande considered I is equal to dz by ds which is equal to sin beta instead of I is equal to dz by dx. So using now again q is equal to kia, q is equal to k sin beta into L sin beta, where KL sin square beta. So being here A, which is the area over which the flow which is taking place, which is nothing but BD into L, where BD is nothing but here, which is sin beta, and which can be written now as A into BD into L, which is L sin beta. So here with this we can write now Q is equal to K sin beta, that is because of the dz by ds into L sin beta. So Q is equal to KL sin square beta. By solving for L, we get now, if you again rearrange the variables and then integrate, then we get, by solving for L, we get L is equal to S minus square root of S square minus H square by tan square beta, where S is the length of the curve A dash BC. That is, from here A dash BC is the length of the curve S. This is the length of the curve A dash BC, which is represented by a small s here. So with 4 to 5% error, we can determine S as root over d square plus h square, where with the 4 to 5% error, we can approximate S is equal to root over d square plus h square. So by knowing S, we can estimate now L. By knowing L now, we can estimate Q is equal to KL sin square beta. That is, L is known and beta, which is the angle here, which is shown here, which is the slope inclination beta. So with that, once L is known, rate of seepage Q can be calculated. Once L is known, now the rate of seepage Q can be calculated. So Casagrande's solution, basically the procedure what we discussed is that the plotting the periodic line for seepage through earth dams. So for construction of flow nets for seepage through earth dams, the periodic line needs to be established first. So what we discussed is that in the flow through an earth dam, the construction of further construction of flow nets, the most difficult part is the construction of a periodic line. Though we have discussed about some methods, they suffer from this limitations, but this particular Casagrande's solution, where to some extent both entrance and exit conditions have been treated correctly, so that we can arrive at a very close to the which is going to occur, that is the periodic line which is going to occur, very representative periodic line which may occur in the feed. So curve A dash E F B dash C is a parabola with its focus at C. So in this particular slide, a dam which is shown, which is having a coefficient of permeability K, and again this distance is 0.3 delta, and this distance is delta, H is the height, and that is the head which is causing the flow, and D is the distance from here vertical axis to this particular point A dash. So here, if A dash E F B dash C is a parabola with its focus at C, the periodic line coincides with the parabola with some deviations in the upstream and downstream phases. So here what he assumes is that the curve A dash E F B dash C is a parabola with a focus at C, and the periodic line coincides with the parabola, but with minor deviations at the upstream and downstream phases. At point A, the periodic line starts at an angle 90 degrees, because this being the equipotential line, and this being the flow, this is the topmost flow line. So, this orthogonality has to be maintained. So, at point A, the phreatic line starts at an angle of 90 degrees. Here at point A, the phreatic line starts at an angle of 90 degrees. So, here the circle portion indicates that the entrance condition which is actually has been considered, which is shown here. So, at point A, the phreatic line starts at an angle of 90 degrees, where at point A the phreatic line starts at an angle of 90 degrees, that is which is shown here. So, while drawing this phreatic line, it has to be noted that while drawing from upstream face, that this phreatic surface has to be started with a 90 degree angle with the upstream face. So, here portion of the phreatic line coincides with the parabola, and then this is the C which is the focus, and C dash is the length P, and this distance is P, and this is the directrix of this. So, B and B dash, this distance is delta L, and this is the small l. So, we will come to this particular because some observations have shown that when the beta angle which is greater than 30 degrees, then it has got some deviations. So, Casagrande has given some methodology where what exactly how to locate BB dash and BC in case if beta is more than 30 degrees. So, Casagrande's solution, if you look into the for procedure for the constructing the parabola, A dash E F B B dash C, that is a portion of the parabola is shown here. C is the focus and D is this directrix, and CC dash is the distance P, and if let CC dash is equal to P, then A is the point on the parabola with the coordinates x and z, and C with the focus coordinates having 0 to 0 0, and AD is this horizontal distance, and AC is this particular distance which is represented between distance between point C and A, that is focus of the parabola, and A is a point on the parabola. Based on the properties of the parabola, we can say that AC is equal to AD, but we can write from this figure AC as root over x square plus z square, and AD is equal to 2p plus x, because this is being x horizontal distance. So, we can write AD as 2p plus x. So, here by equating now AC is equal to AD from the properties of the parabola, we can write root over x square plus z square is equal to 2p plus x. So, we can write now with AC is equal to AD, we can say that root over x square plus z square is equal to 2p plus x. At x is equal to D and z is equal to h, we can write p is equal to 1 by 2 root over d square plus h square minus d. That is here this is for z is equal to h and x is equal to d, we can write now x is equal to d and z is equal to h, we can write this p is equal to 1 by 2 into root over d square plus h square minus d. By knowing d and h, p can be calculated now. So, by knowing d and h, p can be calculated, that is this particular distance, that is distance from the focus to this CC dash, that can be estimated by knowing d and h. With p value, for values of x, various values of z can be calculated. So, x is equal to, again by using this, we can obtain x is equal to z square minus 4p square by 4p. So, with p value, for values of x, various values of z can be calculated. So, when beta less than 30, L can be calculated using L is equal to d by cos beta minus root over d square by cos square beta minus h square by sin square beta. This we have derived earlier. So, the same thing can be applied for beta less than 30 degrees. In case for beta greater than or equal to 30 degrees, Casagrande proposed an approximation here, which is the distance delta L, that is this distance here, and L. So, from the directrix now this location of this particular this thing. So, delta L by L plus delta L for different betas which is given. So, for 30 degrees delta L by L plus delta L is around 0.36, 60 degrees is around 0.32, 90 degrees around 0.26, around 150 degrees beta it is around 0.1 and 180 degrees beta it is around 0. So, after locating B dash B is equal to delta L and BC is equal to L, curve FP can be approximated by drawing by hand approximately. So, by you adopting the procedure, that is by from this upstream phase setting a distance 0.3 of the delta, that is this particular distance which is delta times 0.3 times the delta, and maintaining this orthogonality here and drawing a free curve here for joining FB, we can construct this periodic surface. Once this periodic surface is obtained, now we can use this concept to again adopt the concept of constructing flow net for determining rate of seepage through an earth dam. So, if you look into it, now we have come to the stage where the flow net construction for an earth dam. So, we said that drawing the periodic line or location of the periodic line is a which is very much required for now with the procedures which are discussed is that are based on the Jupyter solution or Schaffernaks solution, or by adopting this Casagrande's method, we can determine the periodic line. Now, draw the periodic line. So, this being known to us, and note that here in this cross section, if you see here a dam which is shown here, and AG is equipotential line and GC is a flow line. So, this is the bottommost flow line, because the flow cannot cross this impervious base, it flows along the impervious base. So, with that in mind, the GC is flow line and AB is equipotential line. There are some deviations here where the orthogonality is again not maintained. So, draw the periodic line. So, this is known. Note that AG is an equipotential line and GC is flow line. Pressure head at any point on the periodic surface. So, this topmost line, by the procedure which are discussed, is going to yield this particular line which is the periodic surface. So, pressure head at any point on the periodic line is 0, because being atmosphere, it is atmospheric pressure, the pressure head is 0. So, pressure head at any point on the periodic surface is 0. Hence, the difference of the total head between any two equipotential lines should be equal to the difference in elevation between points where these equipotential lines intersect the periodic line. So, pressure head at any point in the periodic line is 0. Hence, the difference of total head between any two equipotential lines should be equal to the difference in elevation between points where these equipotential lines intersect the periodic line. So, here for determining the number of potential drops, nothing but now total head, which is H, divided by say number of potential drops which you are trying to give, say number of potential drops say ND. So, total head is say the head loss, which is upstream water head, in this case is H, then H by ND is going to give the delta H, which is the potential drop. So, first procedure is to drawing the amendment to the scale, and then constructing the periodic surface and establishing the periodic surface by adopting the procedures which are discussed in the previous slides. Then drawing the headlines. By drawing the headlines, number of headlines, draw headlines for the cross section of the dam. So, simply draw the headlines for the cross section of the dam with the delta H. It just divide into the number of equipotential drops, and from there draw the flow net. Again, seeing that this being a flow line, so maintain this orthogonality and see that these curvilinear squares are maintained. So, in this case now, if you look into it, the flow is taking place like this. So, again the number of the potential drop lines, they are numbered from this direction to this direction, 0, 1, 2, 3, 4, 5, 6, like this it will come. And when it comes to the flow channels, they are 1, 2, maybe around 2.5 flow channels. So, here by estimating the number of flow channels, number of potential drops, and having known the K, that is coefficient of permeability of the soil which is in the at the bund or at dam, we can estimate the rate of seepage which is actually occurring through this. So, in this lecture, we try to understand how this flow net concept can be applied for solving some typical problems. like we discussed about a long horizontal drain, and we also try to see how the anisotropicity of soil as far as the permeability is concerned can be considered while drawing flow nets, and then we discussed the methodologies which are involved in arriving at a transformed section, and then how this anisotropy can be converted into a transformed section that we discussed. Thereafter, we try to discuss how the rate of flow can be estimated through in earthen dam. So, for that we discussed about three methods: Jupyter solution, Schaffernaks solution, and Casagrande's solution, where we main impetus is to locate the phreatic surface, and then thereafter the procedure is very simple for determining the particularly the rate of seepage through earthen dam. So, here one concept which is required to be keep in mind is that being this pressure along the phreatic line, the pressure it is being 0. So, whatever this total elevation which is there divided by that number of potential drops, directly we can easy to draw equipotential lines in this case. So, the same concept can be used for determining the rate of seepage through this particular medium, in this case having a homogeneous soil which is having a isotropic permeability K. In the next class, we will try to discuss about how these problems can be prevented by providing some filters, and there are some typical failures which are called piping and boiling conditions which are required to be considered for these hydraulic structures, and then factor of safeties which are involved against this for these hydraulic structures against piping failure and by boiling failure. Based on this, we will try to also solve some problems by using this flow net concept for determining the uplift which can be exerted on a particular structure, and how this uplift can be relieved by using some filters and other possible remedial measures will be discussed in the next lecture.